So in this lesson, we're going to look at all of the various naming rules that you'll find in chemistry. We're going to start with binary compounds, which are compounds that are composed of only two elements. And we're going to start specifically with ionic compounds. Now, an ionic compound is a compound that has a metal and a nonmetal that combine in a ratio that gives them an overall charge of 0. So you may have seen this as the crisscross rule previously. So lithium has a +1 charge. Oxygen has a -2 charge, typically. And what we'll do is we're going to bring the value of the charge down, and what that'll give us is our compound. So it'll give us the fact that we're going to need 2 lithiums for every 1 oxygen. So that's the ratio that they occur in. Now the overall charge on this compound, like all ionic compounds, is 0. So 2 positive charges plus 1 negative charge equals 0. And all ionic compounds work that way. It's important to know also that ionic compounds are electrostatic attraction, and they aren't actually a bond. So they're held together by the attraction of the positive and negative ions to one another. Now, in terms of the naming, the metal always goes first, followed by the nonmetal. So well, actually, maybe I'll look at the lithium oxide here. So in terms of the name here, I'm going to do lithium, and then oxygen is the nonmetal. It's going to lose its regular ending, and we'll just go with the stem version of it and put "ide" on the end. Okay, there's a couple examples here for both formulas and compounds. Pause the video, try them, and then come back and we'll look at the solutions. So the solutions are here now. So sodium chloride's NaCl, magnesium sulfide is MgS. Keep in mind that when you do the crisscrossing, you're going to have Mg2S2, but we're going to reduce that to give us the correct answer, which is the MgS. So these 2's basically cancel one another out. Or the +2 charge, you only need one +2 charge to combine with a -2 charge to get a compound with a 0 charge. Aluminum fluoride, AlF3, aluminum sulfide, calcium oxide, sodium nitride. Please note that sulfide can be spelt with an F or a PH. In all of these cases, you'll notice that there isn't any monos, dis, tris. Those are for covalent compounds exclusively. Okay, so moving on. Compounds that contain hydrogen. Hydrogen is a cation, which is the common form. You're going to have hydrogen, and then that'll be basically hydrogen with a nonmetal. And the naming works just like that. So it goes hydrogen and then whatever the nonmetal is. So it could be hydrogen chloride, hydrogen sulfide, hydrogen nitride, hydrogen iodide. Or they're the examples where you have hydrogen combining chemically with a metal. So we got hydrogen combining with a metal. In those cases, it's an anion, and that's going to change the names. So it's going to be the metal name first, and then hydrogen will be hydride instead of hydrogen. So again, let's pause the video, try these examples. I'll put my solutions up, and you can check them. Okay, so looking at these examples here, hydrogen with the nonmetals, hydrogen sulfide, hydrogen nitride. Hydrogen with the metals, sodium hydride, magnesium hydride. Okay, polyatomic ions are another type of ionic compound. So the ion in there should hopefully give that away. But there are actually groups of covalently bonded nonmetals that have an overall charge. And these will combine with metals to form stable ionic bonds. So again, we're going to be canceling out the charges. So the charges of the metals should cancel perfectly with the charge of the polyatomic ion. Now, last year you probably dealt with base radicals, which are just like the common form of the radical or polyatomic ion. So for example, chlorate. Now chlorate actually, and all polyatomic ions that have negative charges have multiple forms. So there is a chlorate ion that has one more oxygen. So perchlorate is the name of it. To have one more oxygen, it's going to obviously, instead of having 3, have 4. Now the thing that won't change when we're dealing with polyatomic ions and their different forms is that the charge on them always remains constant. So all of these vary by the number of oxygens in their compound. So, for example, chlorite is going to be ClO3. Hypochlorite is going to have 2 less oxygens, so it's going to be ClO2, but we'll continue to have the -1 charge. Okay, so try now with the sulfates and see how that goes. So pause the video and try the different forms of sulfate. So here are the different forms of sulfate. We got SO5, 2-, which is persulfate, SO3, 2-, sulfite, and SO2, 2-, hyposulfate. So try with the additional examples we have down below here to name them correctly. You do have a list of polyatomic ions on the backs of your periodic tables. That'll help identify the base form of the polyatomic ion. And you will also need to use that to help identify if you have more oxygens, 1 less or 2 less, which also should be reflected in the name. Okay, so pause the video, try naming these 6 examples, and check back in a second when you're done. Okay, so hopefully you named all what turns out to be 8 correctly. I've put little stars on the ones that have a difference in the radical. So calcium hypophosphate, lithium percarbonate, silver perchlorate are the ones where the number of oxygens actually varies from the base radical. The rest of them should have been fairly straightforward, I'm hoping, for you. Please note that ammonium is, I believe, the only positive polyatomic ion. It differs from ammonia by having 1 extra hydrogen, so NH4, and a +1 charge. If ever you get confused, if you write the 2 names, like ammonia and ammonium, beside each other, ammonium has 1 extra letter. It also has the extra hydrogen and the +1 charge. Moving on to the bi rule. The bicarbonates or bisulfates are basically leftovers from an acid-base reaction. So they're a salt that's formed when certain acids are neutralized. So sodium bicarbonate is also correctly, but much more in terms of like words, named sodium hydrogen carbonate. So sodium bicarbonate and sodium hydrogen carbonate are the same thing. We use bi because it shortens the name up, basically. And it's an example of metal and hydrogen being our cations with a polyatomic ion. We looked a little bit at hydrogen as a cation in the previous page, I believe. And this is another case of hydrogen acting as a cation. So the name for bicarbonates or bisulfates can be one of 2. So it can either be, so for example down here we have lithium hydrogen carbonate or lithium bicarbonate, depending on how much writing you want to do. So you'll see both, just be aware that it is the same thing. All right, so in our transition metals, so the metals that are listed in the middle of our periodic table, they have multiple forms that are stable. So a transition metal can have multiple charges. Not all of them do, which sometimes makes it tricky to identify what the charges are. but many of them do have multiple charges. Things like silver and zinc, you'll find also listed on the back of your periodic table as metals that are hard to find their charges based on their position on the periodic table. And you'll also notice that there are a pile of other transition metals listed there that have multiple charges. Now, typically what we do is we indicate the form that's present in the molecule with the Roman numerals. So iron 2, iron 3, gold 1, gold 3, copper and lead as well. There is an older system that distinguishes between the stable forms by adding suffixes to the old-timey names. So something like cuprum, which is hopefully also on the back of your periodic tables, the old-time names. So what we're going to do is we're going to drop the ending here. So cuprum will become cuprus for the lower version and cupric for the higher version. So in these cases here, we're taking the suffixes or endings and putting them onto the old Latin names. Now, we need to just sort of be aware of this method. It's not popular anymore, but people still label their chemicals this way from time to time. So you just need to be aware of it. I'm going to ask that you use the IUPAC version or the Roman numeral version, but there will be times where you're going to need to use the cuprous and cupric version. Okay, so please, again, pause the video and try these examples here. So what I have here are the formulas for the names that were given. So I've got tin 4 sulfate, iron 3 nitrate, and copper 2 chlorate. I just sort of want to highlight the fact that the tin 4 sulfate, we're reducing the subscripts. And with the nitrates and chlorates here, because we have multiple nitrates or multiple chlorides, we're going to put brackets around the polyatomic ion and then put how many of the polyatomic ion we need. So in the case of iron 3 nitrate, iron's got a 3 plus charge, the nitrate's got a -1 charge. So we're going to need 3 nitrates in order to balance the charge on the iron. And then similarly in the copper, we're going to need 2 chlorates to balance the charge on the single copper. Now, determining the state that the polyatomic ion is in sometimes is a little bit tricky for people. So what you have to remember is the charge on the nonmetal or polyatomic ion. So for example here in the iron oxide example, we know it's iron oxide. I know I've got a -2 charge on oxygen typically. So for me to have a single iron, I need to balance the charges. So the charge that balances perfectly with a -2 charge is going to be a +2 charge. Now, I know it's a +2 charge because I know that my oxygen has a -2 charge. There's 1 iron, and I know that my total, when I look at the charges, has to add up to 0. So 2 minus 2 is 0. So that makes this iron 2 oxide. Now, with practice, this becomes a lot easier. Sometimes it's difficult at the start, but it's a reasonably straightforward process. So pause the video, try the next 2, and see how they go. So the very next example is lead 2 nitrate. Now I know it's going to be lead 2 because the charge on the nitrate is -1. There are 2 of them, which means I have an overall charge of -2 up here. And then the thing that's going to balance out with a -2 charge, if I have a single atom of lead, it's got to be a +2. So 2 minus 2 equals 0, so I have lead 2 nitrate. In the case of the gold nitride, be careful with this because this is a common mistake. Nitrogen by itself, nitride, but we write nitrate a lot more often, so sometimes people make the mistake of confusing the 2 elements here, or the polyatomic ion with the element. So in this case here, I know nitrogen has a -3 charge. I have 3 gold atoms with it. So my gold choices in terms of charges are 3 and 1. The only number that makes sense here is going to be 1. So 3 times 1 is 3, minus 3 equals 0. I've got gold 1 nitride. Moving on, peroxides are sort of aberrations. There are compounds that have one more oxygen than a normal oxide. Pretty much you'll only ever see hydrogen peroxide, sodium peroxide, lithium peroxide. In all of these cases, these are just things you're going to have to remember. You're going to have too many oxygens. So we should only have one oxygen with two hydrogens, but because it's hydrogen peroxide, I have to know that it's H2O2. And it's the same for all peroxides. So sodium peroxide will be Na2O2, and if I had lithium peroxide, it would be Li2O2. Now, we've already talked about binary compounds that were ionic. We're now going to look at covalent compounds. The primary difference between the two is that we actually have a proper bond or shared electrons in a covalent compound. So the electrons are shared between the atoms, forming the bond, as opposed to exchanged in an ionic compound. And the way that we can easily identify them is that they possess two nonmetals. Now, unlike ionic compounds, we're going to use Greek prefixes to indicate the number of atoms in a formula. There's some additional rules with that. We're never going to use mono on the first element of a compound. Sometimes the final O or A of a prefix is dropped when the element begins with a vowel. Now, it asks here, how do you know which element goes first? Basically, you could memorize this list, or you're going to write the names in terms of the way they're listed in the chemical formula. It's not something that you're going to need to worry about too much right now, but one day, if you ever discover a compound, you'll want to write them in the correct order. And that correct order here, though it isn't actually explained, is going from least electronegative to most. So fluorine's the most electronegative element on the periodic table. Boron is the least electronegative nonmetal. Now, pause the video. I think most of you will probably have a fairly good handle on this naming. Try these examples and see how it goes. So these are the names. I got CO for carbon monoxide, N2O3 for dinitrogen trioxide, CCl4 for carbon tetrachloride. Just notice that the NO, there's no mono nitrogen, monoxide. So just remember that there's never a mono at the start of your compound. Okay, moving on to acids. There are two types of acids. There's going to be oxyacids, which we're going to talk about right now, and binary acids, which we'll talk about in a minute. Oxyacids are distinguishable from binary acids because first, like the name suggests, they're all going to contain hydrogen. And basically these are hydrogen bonded with a polyatomic ion. And the simple thing to do here is to take the 8 ending from your polyatomic and replace it with ic. So chloric acid, the next one is going to be bromic acid. So try the next, whatever there is, 4 or 5 there, and check back. So these are the names that are used for all of these acids. Notice that there is no hydrogen in the name, so it's bromic acid, iodic acid, nitric acid. There's no hydro in it. The hydro is going to distinguish between these oxyacids and the binary acids that we're going to talk about in a minute. The sort of naming rule I gave up here with dropping the 8 and ending ic is true for most cases. Sulfuric acid and phosphoric acid, you also have to add some other letters like the UR and OR to sort of get your correct name. Now, just like in regular oxyacids, we're going to have oxyacids that have less or more oxygens. And we're going to deal with it in the exact same way, so we're going to change the suffixes. So if it has 1 less oxygen than the normal polyatomic ion, we're going to call it aus. So it'll be like sulfurous acid. 2 less, we're going to continue with the hypo that we used in the first part, or with regular polyatomic ions, and have the aus ending. And just like with the polyatomic ions, when it had more oxygens, we are going to use the prefix per with the standard ending, ic. So try these examples down here. You're going to want to look at your polyatomic ions sheets again and just sort of give these a try. So pause the video and try them and then check. Okay, so I just wanted to maybe mention the fact that the charges, I just want to remind you, I guess, that the charges, just like when the polyatomic ion loses oxygens, the charges don't change. So sulfurous acid is going to have one less oxygen, but still going to have a -2 charge. So we're going to get H2SO3. Something else I just sort of want to emphasize right now before I finish the rest of the examples here is that sulfurous acid, like all acids, needs to have an aqueous at the end. Acids don't have the characteristics of acids until they're dissolved in water, and that's what the AQ lets us know is happening. So, I'm sorry, try the rest of the examples here. If you've already tried the rest of the examples, just let the video play, but I'll put up the rest of the answers in just a second. Okay, so here are the rest of the acids correctly formulated. Please do note that we do need the aqueous after. So these are the correct names here. I feel like it's reasonably straightforward if you understood the polyatomic ion thing. So less oxygen, same charge. So that means we're going to have the same number of hydrogens for both phosphorus, hypophosphorus, and perphosphoric acid. All right, so to take a look at binary acids now. So binary acids form when certain gases dissolve in water to form an acid. These names do include the word hydro. So the difference in naming is that hydroic acid is going to be simply a nonmetal and hydrogen. So it's going to be hydrogen with a nonmetal as opposed to hydrogen with a polyatomic ion. Now typically the nonmetal it's with is going to be a halogen. So it's going to be often with chlorine, fluorine, iodine, or bromine. Sometimes it can also be with sulfur. So the gas names for these, so HI would be hydrogen iodide. So as a gas, it's called hydrogen iodide or hydrogen bromide. But to make it an acid, just like before, I'm going to be dissolving it in water. So if I filled a room with hydrogen iodide gas, it wouldn't act like an acid. As soon as I put water in the room and the hydrogen iodide gas dissolved, I would then end up with hydroiodic acid. And the difference is going to be the state, so gas versus aqueous. So this is going to be hydrobromic acid. Okay, finally we've got our hydrates. Now hydrates are basically ionic compounds that have water molecules trapped in their crystal structure. We'll spend some time studying them towards the end of the second unit. Now, basically the way these are named is you've got two parts to your name. You've got the ionic solid parts, which are separated from the waters by that dot. So you're going to name the part that I have boxed in here in red normally. So pause the video and just write down the names for these three salts. So hopefully you recognize that copper and iron are transition metals and identified the charge they had appropriately. And now the last part here is going to be the hydrates. So you'll notice just by the formula that the hydrates are sort of separate from the ionic compound. So what we're going to do now, so for the first example here, I've got copper 2 sulfate. Now I've already told you that these are called hydrates. Now what we're going to do is now account for the 5 waters. So we're going to use the Greek prefix for 5, which is penta, and the Greek word for water, which is hydrate. So I've got copper 2 sulfate, pentahydrate. The next example here, I've got 2 waters attached to my barium chloride. So I've got barium chloride, dihydrate. And finally, iron 3 chloride, which is with 4 waters, is going to be tetrahydrate. And that's basically all of the naming stuff that you need to know for grade 11 chemistry. Hope you've enjoyed.